Hello, good afternoon. This is Chetan Jain from ISHRAE HQ, New Delhi office. I welcome all of you in webinar on overview of HVAC system by our experienced HVAC professional, Mr. Sandeep Dahiya. Mr. Sandeep Dahiya has done B Mechanical and MBA from Pune University and having more than 15 years of experience in HVAC industry. He is a lead EP and a certified measurement and verification professional. He is also BE certified energy auditor and a BEAP. Right now, he's self-employed and works as a energy engineer. I would also like to inform you that the question and answer session will be conducted in last 15 minutes of this webinar. So you can, post your question in the question tab. Now I would request Mr. Dahiya to start the webinar session. Thank you.
Okay, thank you, Chetan. So Chetan, are you able to see my screen?
Yes, sir. Yeah, I'm able to see you, sir. Yes, your screen.
Okay. So is the presentation, can you view the presentation now?
Yes, sir, I can view the presentation. This is ISHRAE webinar overview of HVAC system.
Correct. All right, great. So we are all set and I think I can start, right?
So, sure.
Okay, thank you. Okay, welcome everybody. I can see a lot of participants on the call, and it's great to get a chance to speak to all of you. The topic of the webinar, as you can see, is an overview of HVAC systems. To be frank, I will not be talking too much about the H and the V of HVAC. I'll be focusing more on air conditioning systems, and that too, I would be focusing on a particular kind of air conditioning system, which is basically comfort air conditioning, which is what we end up doing in buildings. So that's the focus of this presentation. Why did I choose this topic, and why do I think it is important, especially for the youth which is joining ISHRAE or joining the HVAC industry? It stems from my own experience, and which was that I've got about 20 years of experience in HVAC now. I worked with various equipment manufacturers. I was working with Alfa Laval, and that was the time when I used to sell evaporators, heat exchangers, which were being used as evaporators and condensers. Then I joined Thermax, and Thermax was all about vapor absorption machines. Then I joined York or Johnson Controls, and that was about screw chillers, centrifugal chillers, and even airside equipments. But to be frank, even after 10 years, I did not have the full view of what is actually happening in a central air conditioning system. So what I'm saying is, this is from my own experience that I was focusing only on an equipment and probably was not, properly aware about the whole system. So that's the reason I chose this topic, which is that, yes, if you guys are joining the HVAC industry, air conditioning industry, you should understand the whole system. You should have an overview of the whole system. Second reason of choosing this topic is that we talk about HVAC, we talk about buildings. HVAC is one of the big energy guzzlers in a building, and hence an HVAC system needs to be efficient. As Chetan was introducing, since last about 4.5, 5 years, I work as a freelance energy engineer, and I basically audit HVAC systems, and I help clients run their HVAC systems more efficiently. And what do I see? I see a lot of inefficiency in the way HVAC systems, one is, are being designed or commissioned, and second is, or in a bigger way, is in the way they are being operated. So these are the two aspects which I had in mind when I chose this topic. So let me go ahead and dive right in. When we talk about comfort air conditioning, there are these various kinds of HVAC system. A very simple window AC and a very complex central chilled water system. So you got a wide variety of HVAC systems. When we talk about HVAC or air conditioning, in particular, space air conditioning or comfort air conditioning, one tends to think that the most important thing is maintaining the space at a particular temperature and RH. But that's not it. There are other attributes to an HVAC system, which is you should even have air movement, which is happening in a space properly. So we've got mixed air systems, and the supplier is supposed to mix in the air properly, in the space properly. Otherwise, what you have is something called hot spots and cold spots. Secondly, we've got people occupying a building and they are breathing. And if it's a closed building, which it is, because that's how we are conditioning it, their CO2 levels are rising, and we do need to bring in adequate amount of fresh air. We don't want to make a building a sick building. I mean, the whole reason that we were doing comfort air conditioning was so that people can be more productive in doing their desk work, and hence there needs to be adequate amount of ventilation or fresh air which gets introduced, so that people can be more productive. I mean, they don't there's something called a sick building syndrome. If the CO2 levels are high, you would feel lethargic, you would not be productive. Clean air is also very much a consideration of an HVAC system design. I should say more prominent now. I mean, in Delhi NCR, all that we talk about during winters is PM 2.5 levels. And hence, for an HVAC system, it is even required that you maintain, clean air inside these spaces which you are conditioning. And last but not the least is that your HVAC equipments which you're installing should not be leading to higher noise levels, which again leads to loss of productivity. You're aware we are now designing a lot of green buildings, and from an architecture perspective, which also affects productivity in a way, is that we are talking about that any building or any space that we are trying to construct, there should be natural light which comes into the space. These windows help us in getting natural light, but also there's a disadvantage that when you have an all glass building, for example, you've got a huge amount of heat load also. Second is, if there are views, a person working in a space would again be more productive. So what I'm trying to tell you is, it's not only temperature and humidity, and we are looking at all these various attributes. Now, these different air conditioning systems, whether you take a window AC or whether you take a complicated central plant, they are able to meet these requirements differently. Some systems are able to meet them better, and some systems are not able to meet some requirements at all. All right. Now, when you walk into a centrally conditioned building, understanding an HVAC system sometimes seems too daunting or too challenging. And the reason for that is you don't end up seeing the HVAC system as one. You might walk into the basement and you might see a chiller plant room, and you might see chillers out there, and you might see a lot of pumps and piping. Maybe you go to the rooftop and you would see some cooling towers installed there. You go to a space, you might see an air handling unit. You might see a lot of ducting running everywhere. You might see risers. So you are seeing the whole system in bits and pieces. Probably that's one of the reasons why people don't comprehend an HVAC system properly. So the best way to understand HVAC systems is that we should break it down into subsystems and look at how each subsystem is interacting with another subsystem, and how the whole thing is working properly as one. So these are the various subsystems which can be there in a central plant. You would have an airside system or an airside loop that's interacting with something called a chilled water loop, which in turn is interacting with something called a refrigeration loop, which in turn is interacting with something called a heat rejection loop. And to run all the whole system as one, you would have a controls loop which is sitting on top of all of them to make sure the whole HVAC system runs as one at its most efficient in the most efficient manner. So let's go and look at each of these subsystems. First, the airside loop or the airside subsystem. So what do we have? We have a space which we are trying to condition. So we're trying to maintain the space at a particular temperature and RH. Now, what's happening is, because it's a closed space, this space is having some heat gains. These heat gains are some of the heat gains are sensible in nature, and some of them are latent in nature. What we are doing when we are designing an air conditioning system is we are sending a certain quantity and quality of supply air. And the job of the supply air is to come into the room, absorb the instantaneous, sensible, and latent load. And then we even have a return air which is going back to the equipment. So that's what we are trying to do in a space. Now, to talk about these loads, as I said, a space has a sensible heat gain and a latent heat gain. Just to quickly, or in one slide, tell you what can be the various loads. So imagine this room, which I want to condition. So I want to maintain it at, say, whatever, 75°F, 50% RH. I'm going to obviously design the system based on summer conditions or monsoon conditions, whichever is the worst. Imagine this room as a single story building. We are talking about this room, so it's got this roof here, an external wall here. That's an internal wall, or maybe some other space here which is not conditioned. So imagine this. So what are the gains which are happening in this space? So you've got outside ambient, which is at a higher temperature than the temperature being maintained here. So you've got a conduction heat gain, which is happening through the roof, through this exterior wall, through this glass also. So that's your exterior loads, conduction heat gains. Then you've got, your sun shining outside, your sunlight coming in. And so you've got, a solar radiation heat gain, which is happening in this space. As you're aware, radiation is a heat transfer which happens, which does not heat the medium, but would directly heat an object if it is at a different temperature, So you have got the sun, which is heating all these various objects. Wherever the sun is directly seeing, it's heating all these various objects. So that's your solar radiation heat gain for this space. That's happening because of your windows or maybe because of your skylights. Then you've got conduction heat gain happening through these unconditioned spaces, maybe a partition wall over here, a floor over here. Then you've got your internal heat gains, which is nothing but humans. We are a load. A human body is being maintained. Our body is trying to maintain a temperature of 37 degrees C. So what's happening is we are always rejecting heat, and we are rejecting both sensible and latent heat. So people are adding load to a space. We've got lights, which is adding load. We've got equipment, which is adding load. Plus, there might be leakages. So we might have infiltration. So these are all various loads. Most of the loads are sensible in nature, and some of them are latent. For example, infiltration would have a sensible and latent component. A people load is both sensible and latent. Lights are all sensible. Equipment is all sensible. Conduction heat gain is all sensible. So we try to calculate the sensible heat gain and the latent heat gain, and that's our starting point for the design of an HVAC system. Now, so this is what is happening. We would like to deliver a particular quantity and quality of supply air into this room. The job of the supplier is to absorb the instantaneous heat load of this space, which is the sensible and the latent. Then we've got our return air going back to the equipment. So that's our return air. Some part of the return air is being exhausted because we've got people occupying the space. We introduce some amount of outside air. So the return air mixes with the outside air and becomes something called mixed air. This mixed air we are passing over filters. We want to maintain clean air over here. We are passing it over an equipment called a cooling coil. The job of the cooling coil is to cool and dehumidify the air. We're going to talk about that in a second. Then we've got a fan, and then we've got our supply ducts. So the fan, the ducts, it ensures that we are supplying the desired quantity of supply air into this room. What's a cooling coil? Cooling coil is nothing but a heat exchanger. What you have is copper tubes and aluminum fins. So in the tubes is chilled water or maybe even a refrigerant. But let's right now imagine that this is a chilled water system. And so you've got chilled water flowing through these tubes and you've got air passing over this. So what happens in the cooling coil is you've got warm, humid air which passes over the coil. It cools and it is actually being cooled below its dew point. So once the air is cooled up to the dew point and then cooled further, the air cannot hold any more moisture. And that's the time when the moisture starts condensing. And that's how you have a wet coil. And ultimately, what comes out of the coil is cool, dry air. Although the RH of the air at this point of coil condition is going to be 90 to 100%, it is dry because the absolute humidity or the specific humidity has come down. So what is happening in this process is cooling and dehumidification. Now, we might design, a system and we might calculate the peak load, but the load of the space is continuously varying. That's the nature of an air conditioning load, and you can understand why that is the case. Once it's not that hot outside, obviously the conduction heat gains are lower. If it's cloudy outside, the radiation heat gain is not there. If the occupancy is not as per design, the loads are lesser. So the load in the space is continuously varying. So you are obviously, we want to maintain the space at a particular temperature, and what that means is if the load is lower, I must not, supply the same quality and quantity of air, and I must control it because there's no point in overcooling a space. That would be a waste of energy, right? So there are these two ways I can control this airside loop. Now, first way is what is the most conventional way, which is still being used a lot here in India at least, and that's called a CAV system, which is a constant air volume system. As the name tells you, what it means is that the quantity of supply air which I'm giving to the space remains constant irrespective of load. So if the load is lesser, what do? I basically raise the supply air temperature. So the supply air temperature is higher when the load in the space is lower. I'm going to tell you how that happens in a minute. But this kind of a system is what is called constant supply air quantity, variable supply air temperature. So this is a CAV system or one of the methods of controlling the airside loop. The other method, which is more efficient, and as I said, in HVAC, we are focusing a lot on the efficiency aspect because HVAC systems consume a lot of energy and we would like to optimize it to the maximum possible extent. So, as I said, the load here is variable. Now, the other system, what that would do is called a VAV system, a variable air volume system. So, as the name suggests, what I'm going to do is, if the loads are lesser, I'm going to vary the quantity of supply air which I give to the space. But the temperature which comes to the space remains constant. So the supply air temperature remains constant, but the supply air volume is reduced if the load is reduced. And how do I do that? We put something called a VAV box. This is one of the methods of doing it. So there would be a room air temperature which directly controls this VAV box, and accordingly the amount of supply air coming into the room is controlled. As the VAV box closes, the duct pressure here increases. I am sensing that, and that controls the speed of the fan. So this is how a VAV system works. A VAV system turns out to be more energy efficient as compared to a CAV system. Uh, this is a typical schematic or, a 3D diagram of an air handling unit. It's not that an air handling unit would always be this kind of a construction, double decker. This is just one example. It could all be a single decker construction also. What you see in this air handling unit is first a mixing box. A mixing box is where your outside air and your return air is mixing. Then this mixed air is passing over the filters. We're going to have a fan. We're going to have a cooling coil. In many commercial buildings, if you were to go, you will find they are using floor mounted air handling units, and you would find AHU rooms. So in many buildings you will see that the AHU room itself is actually a mixing box, and the typical construction of an AHU is nothing but a filter, a coil, and a fan, and you may not find this mixing box in many AHUs. Okay, so just to show you what the supplier distribution systems looks like. So we've got our outside air coming in. Obviously, there might be a fan which is making sure that I supply the required amount of outside air to this unit. I've got return air coming in through the plenum, supply air, return air fresh air, return air mixing, passing through the coil. What you can see here is four pipes. So this is when I have both, separate pipes for chilled water and separate for hot water. Mostly you will find that, we are in the tropics. And for us, air conditioning basically means cooling. So you will only find two set of pipes, which is basically a cooling coil and not really a heating coil. This is where cooling and dehumidification is taking place. Then I would have a fan, maybe I would have a plenum, and then I've got this duct. Then I would be taking these branches. If it is a VAV system, I would have a VAV box, and then I would have some amount of flexible duct, and then these diffusers, which are directly sending the supply air into the space. So this is what it looks like. I've got a duct coming in. Ultimately, from a diffuser, I have got supply air being introduced into the space. This supply air is not supposed to directly dump. It is this diffuser design is such that it leads to something called a cannula effect. And what happens is the air comes down, goes up, and it properly mixes. My return is not ducted mostly in buildings, and what I have is a plenum. So I've got a false ceiling. So this is my false ceiling, and I've got this return air grills or diffusers, and then I've got my return air passing through this plenum back to the AHU room. So that's what is happening in this air loop. The cooling coil is nothing but a heat exchanger. So what is happening if on one side I have got air being cooled and dehumidified, which is basically its enthalpy is decreasing. So it has done heat exchange. And where did this heat go? Basically, this heat got transferred to chilled water. That's what I had in the tubes. That's your typical design condition. So you've got chilled water coming in at 44 degree Fahrenheit, going out at 54 degree Fahrenheit. So this is what is happening in the cooling coil. Heat is moving from the air loop to the chilled water loop. And I've got water getting heated up. So if this loop is supposed to run continuously, obviously this room is also supposed to run continuously. And I must have a mechanism to cool this 54 back to 44 and send it back to the cooling coil. And that's where the evaporator comes in. So I've got 54 degree Fahrenheit chilled water going to the evaporator, getting chilled back to 44, and then I want to send this water back to this cooling coil. Evaporator is where chilled water is exchanging heat with the refrigerant. That's what an evaporator looks like. This is a photograph of a DX shell and tube evaporator. So DX is direct expansion. What we have is chilled water on the shell side and refrigerant on the tube side. When we talk about more efficient chillers, they don't use a DX shell and tube evaporators. They are all using flooded and falling film, which is that the connections are reversed, which is what you have on the shell side is a refrigerant and what you have on the tube side is chilled water. Anyways, what's happening is that chilled water loses its heat to the refrigerant. So water coming back at 54, getting chilled to 44. And what you have is low pressure liquid refrigerant flowing through these tubes, absorbing the heat, becoming vapor, and then this low pressure vapor going back. So that's what is happening. Now, as you're all are aware, this heat always moves from a higher temperature to a lower temperature. So the temperature of refrigerant, which is evaporating the tubes, has to be lower than the chilled water supply temperature. So that's what is going to happen. Now, I want to make the water flow from the evaporator back to the cooling coil and then back. How do I do that? Obviously, I'm going to need a pump, and that's where this chilled water pumps come into the picture. This control valve is nothing but to control the capacity of this cooling coil. This kind of pumping which I can have, chilled water pumping, are of various kinds. When we were not bothered about energy long time back, the kind of system which we used to use was primary constant. That means these pumps used to send a constant supply or flow of chilled water irrespective of load. We are aware HVAC system consumes a lot of power, and we are all very energy conscious now. So you've moved away totally from primary constant system good about 12, 15 years back. Now the kind of systems you will see in buildings are primary secondary, which is primary constant variable secondary. Basically what it means is that the chillers work at constant flow, but the building is supplied varying flow rate. So that's primary secondary. People are now even designing variable primary plants because there is no such limitation. A chiller can run with varying chilled water flow rate also, although the whole system needs to be fully automatic, and you need to be careful about things like rate of change of flow. So what I'm just trying to tell you is, how do you make this system more efficient, this chilled water loop more efficient? These are the various ways. I mean, what gets utilized mostly in buildings is primary, secondary, with or without zoning, or variable primary. These are efficient. This is not efficient and not used anymore. Okay. So what happened was that the heat of chilled water has now moved to the refrigerant, and that's where the refrigeration loop begins. And how did this heat move? Because you had refrigerant which was at a lower temperature, evaporating at a lower temperature, and hence the heat moved from a higher temperature to a lower temperature. That's always how the heat is going to move. So what's happening in the refrigeration loop is you've got low pressure liquid refrigerant absorbing this heat and becoming low pressure vapors. So what I have at the outlet of the evaporator is low pressure vapors. These low pressure vapors go to something called a compressor. The compressor could be of various kinds. You could have a compressor which is the age-old one is reciprocating type, which we are not using in air conditioning industry anymore. It could be screw or a centrifugal. Scroll is smaller capacities. Screws is larger capacities, maybe up to say 400 tons, and larger than that is centrifugal. So based on size limitations and even efficiency, we've got these various kinds of compressors. Recips are not being used anymore, at least in air conditioning. Scrolls in smaller capacity, or even in VRF systems. The chillers, which you will mostly see in the field, would be either screw or centrifugal. So the compressor, what did it do? It converted this low pressure vapor into a high pressure vapor. And why did I do that? I did that because once the pressure is increased, the saturation temperature of the refrigerator is also increased. And hence, I would be able to condense these vapors with whatever is the cooling medium which I have. So these high pressure vapors go to a condenser and condense. That means they change phase, and that's why it's called a vapor compression cycle. They change phase. That means they convert from a high pressure vapor into a high pressure liquid. This condenser can be of two kinds. It could be air cooled or water cooled. When I say an air cooled condenser, basically what I mean is I'm going to use ambient air, whatever is the outside air, I'm going to use that. And I'm going to, I'm going to have this coil, condenser coil. Ambient air flows over the coil and the refrigerant is condensing inside. So I'm condensing the refrigerant with the help of ambient air. I could do this, or I could use cooling water, which is water from a cooling tower. So I could use that. And this is called a water cooled construction. So in case of a water cooled, what I have is a shell and tube heat exchanger. I will always have water on the tube side. I'm going to have vapors on the shell side. So vapors coming in, condensing over the tubes, and then ultimately they're settling down out here. And at the bottom, what I have is liquid refrigerant, which is refrigerant which has changed phase from vapor to liquid. So once I convert this high pressure vapor to a high pressure liquid, then I pass it through an expansion valve to convert it back to lower pressure. Why do I want to do that? I want to do that because once I reduce the pressure, the evaporating temperature reduces, and I will have to make this temperature lower than the chilled water supply temperature. Then only heat transfer would happen. There can be various kinds of expansion devices. The most conventional one would be a TXV, which is a thermostatic expansion valve, not really used in chillers anymore, especially except smaller chillers. You would see chillers mostly using an electronic expansion valve or some kind of an orifice, fixed or variable. Variable is more efficient. So this was the whole refrigeration cycle or the refrigeration loop. I'm showing you these components separately, but we do not, I mean, especially in buildings, We are not really assembling all these components in the field. What are we doing? We are directly buying something called a chiller. This is what a water cooled packaged screw chiller looks like. So you can see these two set of heat exchangers. One is a condenser, the other is an evaporator. You can see the motor and the compressor here. This is what is called a twin screw compressor. What you cannot see in this picture is that there is going to be an expansion valve, but that is down below. So this is what a chiller looks like. As I said, we no more field assembling chillers, except when they are very large in size, maybe for a district cooling plant or something. All right. So if we were to consider the system to be using a water cooled chiller, so what's happening? We've got refrigerant which is condensing. So if something is changing phase, that means it is giving its heat. Where did the heat go? The heat went to cooling water, and obviously the cooling water got heated up. So these are your typical temperatures for a Delhi-like design condition. So you've got cooling water coming at 90°F, getting heated up to 100°F. So if I've got water, cooling water, which got heated from 90 to 100, I must have a method or a mechanism to cool it back from 100 to 90 so that this heat rejection loop can run continuously. And how do I do that? I take this 100°F water and I put it into something called a cooling tower. This is what a cooling tower looks like. This is a picture of an induced draft cooling tower. So what you have is a fan on top. This is inducing a flow of air over these fills. These fills are nothing but a kind of a heat transfer surface, which is making sure that the contact time between water and air is increased. So I've got water which is coming back from the condenser being sprayed over the fills, and so water is coming down, air going over, and these water I break it into smaller particles to increase the surface area. And now I've got a heat and mass transfer happening between air and water. And what actually happens in a cooling tower is some amount of water evaporates and cools the balance water. So ultimately, I've got water which got cooled back to say 90°F. This is what I'm going to take back to the condenser. So that's my loop. Now, how do I make the water flow from the condenser to the cooling tower and back? Obviously, I'm going to need a pump. So that's where your condenser water pump comes in. So this is what your water cooled central plant system looks like. Now, are all the HVAC systems like this? Well, not really. I mean, as we were just discussing, this condenser could be air cooled. So this brings us to the next variation of this system, which is instead of using a water cooled chiller, you would use an air cooled chiller. Now, what's happening in an air cooled chiller is that there is a condenser coil and I have this high pressure refrigerant condensing directly with the help of ambient air. So that's air cooled. The reason why we would not like to use air cooled is that this system turns out to be not efficient. The power consumption is much higher. So apart from applications wherein the conditions are favorable or the operating hours are lower, or you do not have trained manpower to operate the system, somebody might look at air cooled chiller as an option. But if someone was concerned about efficiency and if water is available, the natural choice is to go in for a water cooled system. So here's an example that you do not have a heat rejection loop, and the condenser is where your refrigerant and the ambient air is directly interacting with each other. It's not necessary that you would have a chilled water loop. There are systems wherein even this is not there. Now, how would you do that? You would do that by designing something called this cooling coil. Now is cooling and dehumidifying the air on one side, but on the other side, you will not have chilled water getting heated up, but you would have refrigerant which is evaporating. So this doubles up as a cooling coil as well as an evaporator. Okay, this is how you can avoid the chilled water loop. So the system becomes like this. So I've got air being cooled and dehumidified on one side, and I've got refrigerant evaporating on the other side. And I might directly use an air-cooled condenser or an air-cooled condensing unit. And this is what a DX system looks like. So this is what is a direct expansion air-cooled system, or ductable systems, as people use the term in the industry. So a ductable system is like this. That's the construction of a ductable system. Now, ductable system would use one-on-one. That means one condensing unit connected to one cooling coil. So we've had there's been a different kind of system, which is, it is not necessary that each indoor unit needs to have a dedicated outdoor unit, and you could have one outdoor unit which can get connected to multiple indoor units, and that system is what is called a VRF. So you've got one outdoor unit connected to many indoor units. So this is what is a VRF, or a variable refrigerant flow system. When you say VRF, basically what you mean is the compressor are with an inverter drive, and hence the flow of refrigerant is varying, and that's varying because you're varying the capacity of the compressor. Lastly, sitting on top of all of these loops is a control loop. As I said, these are loops which are subsystems, but ultimately this whole thing is the HVAC system, and you need a control, a system level control on top of all these loops, so that you can run the whole system efficiently. You might have a thermostat which basically maintains the temperature here and controls this valve. You might have a secondary pump VFD controller which controls the flow of these pumps. So these are called unit level controls. This is what is a chiller. A chiller might have its own control panel. You might have a separate control loop which cycles on and off the cooling tower fans, but you do need an overall system level controller to make sure you run the system efficiently. This becomes very important for HVAC because, as I said, in air conditioning, the loads are continuously varying. So the way you operate a system would change from season to season. Your set points would change. You would want to optimize. You would want to make sure that your system runs efficiently at all load conditions. For that, a BMS is a must. Okay. All right. So what I was trying right now explaining to you is that air conditioning is all about heat transfer. I've already told you that heat moves from a higher temperature to a lower temperature. And this is what we were doing. Cooling coil was nothing but a device wherein heat was being transferred from the air loop to the chilled water loop. Evaporator was a device wherein heat was moving from the chilled water loop to the refrigerant loop. Condenser was a device wherein the heat was moving from the refrigerant loop to the heat rejection loop. Cooling tower is nothing but a device wherein heat is ultimately moving from the cooling water to the atmosphere. All right. So that's what air conditioning is all about, Uh, all these loops need to be optimized. It is not that you just need an efficient chiller. If that's not how you're going to have an efficient HVAC system. So all these loops, airside loop, chilled water loop, refrigerant loop, and the heat rejection loop, all of them need to be optimized, not just one equipment. We must understand that any change or any problem in one loop is going to affect the other loop. So if you got a cooling tower which is not working well and is giving you higher cooling water temperatures, it is going to derate the chiller, which is going to lead to higher chilled water supply temperatures, which is going to lead to uh, cooling and dehumidification not happening properly. So we must understand this. Last and most important is this one word which you will hear in the HVAC industry a lot, which is called optimization. As I said, the loads are always varying. You want your system to run efficiently at all load points, and you're not just trying to make an efficient equipment, but an efficient system. So I've been using this word efficiency again and again, but for the systems which are installed in the field, do we actually even know their efficiency? And you would just have to visit these plants to understand that, yeah, I mean, mostly we don't. And why is that? There are no meters in place. We are not measuring the actual output of a chilled water plant. So mostly we don't know our efficiency. And that's one of the reasons why we become inefficient. So there's this line which is, you cannot manage what you don't measure. This is one of the reasons for inefficiency. I'm going to talk about that in a minute. So if I really want to find out, I mean, I'm just, I'm just going to go back a few slides. Now, if I look at this whole system, the air side loop changes from application to application because your filtration requirement would change. Maybe for a hospital, you're going to have a completely different kind of filters. So the air side power consumption changes from application to application. But this side, which is basically the chiller plant room, sort of remains same for comfort application. So the way the market has started talking about efficiency of HVAC systems is by talking efficiency of chilled water plants. So that's your chilled water plant, your chiller, your condensed water pump, your cooling tower fan, your chilled water pump. This whole thing is what's the consumption is the chiller plant energy consumption. You want to measure what's the output of the chiller plant. Obviously, the output of the chiller plant is nothing but how much tons you are generating. So you've got flow and you've got delta T. So if we were talking in English units, if you know flow in GPM, you know delta T in degree Fahrenheit, then the tons of refrigeration generated by this plant is nothing but flow into delta T divided by 24. You want to find out the energy consumption of each of these devices. You want to total all this, and that's your total power consumption for the plant. That would be in kilowatt. So ultimately, we want to find out kilowatt per ton for chilled water plants, and we want to compare it. So this has become a benchmarking tool, and this is how people talk about efficiency for chilled water plants. And what you can see is there are efficiencies from 1.2 kilowatt per ton right down to 4.3 kilowatt per ton. I'll tell you from my own experience, what do I see? What efficiency are chiller plants running in the field? We would have the best of class somewhere at zero point 0.6. So this is average kilowatt per ton for the whole year. So zero point 0.6 kilowatt per ton. You would even have many buildings which are run at 1.2 or even higher kilowatt per ton. So what am I trying to show you? I'm trying to show you that there's a huge difference between how people are operating HVAC systems. And some of them are operating very efficiently, and in some of them, there's a huge potential to save energy. I mean, and that's basically the reason I have a business. That's basically the reason why I started as a freelance energy engineer, because I see a lot of inefficiency in the field. Okay, so why do you have inefficiency? One of the reasons would be that a plant would have a little higher kilowatt per ton because somebody just bought the minimum efficiency equipment, so not the highest possible COP. Equipments were applied incorrectly. Maybe nobody calculated the pump heads or the fan static requirements, and everything is oversized. So oversizing is one of the biggest reasons for inefficiency. Third is people were focused on the equipment but not on a system, and hence no system level commissioning is done. There are plants wherein you only do reactive maintenance. That is which is called breakdown maintenance. Something breaks down, you do something about it, otherwise you just keep it running. You've not even thought of optimization because you were not even measuring. So if you're not measuring, you're not even thinking about optimization. You're not tracking your data. So one is this kind of a plant will have higher kilowatt per ton, but the bigger issue is that its kilowatt per ton will increase with time and they will not even realize it. Why is that? That's because of something called performance drift. That is, efficiency is going to degrade. Why would that happen? Some drift is natural. One of the biggest reason for drift is fouling of heat exchangers. So your cooling coil can get fouled, your condensers can get fouled, your evaporators can get fouled, but your cooling tower fills may stop, maybe fouled. So that's one reason. You might have your control loops, but they've gone out of tune. You do need to set them right. So your logics are not working well, equipments are not being controlled properly, Sensors are giving you wrong readings. You got one equipment running, the balance equipment, the valves are supposed to be closed, but they are leaking, or an AHU control valve, which is being given a command to close, but it is not closing. Some drift also happens by deliberate action. Stuff like set points are overridden. The whole commercial buildings, they are being run based on complaints. So you got a complaint and the technician just overrides a set point. Chillers were designed at 44 degree Fahrenheit, but are being made to operate at 42 degree Fahrenheit, which is nothing but inefficient. Variable speed drives are ill maintained, or you were having problems or flow issues, and hence you locked those VFDs, or VFDs were ill maintained, cards had to be replaced, you've not done that, and they are being bypassed. Equipments are being ill maintained. There was PID logics which were there, but they have been disabled. So these are all reasons for drift. And since you are not measuring your efficiency, you don't even realize. But what actually happens is that you become inefficient. And with time, your 0.95 kilowatt per ton has even become 1.3. So what I'm telling you is that that in a building, an HVAC system might even be running at 30 to 35% more inefficiently as compared to as it was commissioned, and why do people not realize this huge drift? 30 to 35% or 40% is huge. Why? Because all of these chillers, all of these HVAC systems are oversized. They've got more capacity than their loads, and they keep running their equipments without realizing that their equipments are derating, not giving them output, and their efficiencies are poor. Well, it's not that
Hello.
all the commercial. Yes.
Sir, sorry to interrupt you. I think
Yeah.
we have more 13 or 14 minutes something. So I think we can, after 5 minutes or 10 minutes, we can start the question answer session.
Sure. I mean, I'm just going to
Yeah.
take another 5, 7 minutes to finish
Sure.
my presentation, and then we can continue with the questions. Thank you.
Right. Yeah. Thank you,
All
sir.
right. Yeah. So, apart from these typical commercial buildings wherein maybe the operator was not bothered about efficiency at all, it's not that all the buildings are like that. Most of the buildings are, people are conscious about efficiency, have bought equipments of at least mid-level efficiency. There are consultants involved. There are contractors, HVAC contractors involved. They've done a decent job in applying these equipments properly. The whole system has been commissioned properly and handed over to a facilities management team. For example, you've got AMCs in place and you're doing plant maintenance. You've got your logics which were properly commissioned and are working. Every quarter or something, the facility manager is keeping track of efficiency. So if you're doing all this, you do end up hitting, commissioning a plant at a lower kilowatt per ton. But if you are not doing real time monitoring, what happens is there is still a performance drift. That means from 0.65 kilowatt per ton, you again end up reaching zero point 0.9 kilowatt per ton. So whenever you become so inefficient, and since you are doing your periodic checks, maybe after a couple of years, you will realize, hey, I need to bring in an energy auditor. And that energy auditor is going to check what all is wrong with the system. He's going to set it right. So he's going to set it right. You're going to become efficient again. But with time, because you still don't have real time monitoring in place, you will become inefficient. So what I'm trying to highlight is these areas of inefficiency, and they are huge. 0.65 becoming zero point 0.9 is huge, and it is a fact. I've audited enough plant rooms to know this to know this. All right. So this is also not a very good method of operating an HVAC system. It would again be inefficient. You can do an audit every 3 years and recommission a system, but you have still lived with inefficiency. And that brings us to the best kind of an HVAC system which can be installed. Obviously, you will end up using the highest quality equipments. You will apply them properly, whether it's a variable pumping system or it is VAV boxes for your airside loop, your cooling towers which are sized correctly, your water treatment which is working properly. Then you would have your data recording and analytics. Means you would have your MNV in place. You would be measuring and know and be always aware about your efficiency levels, because you have so much of data that will help you in doing something called predictive maintenance, which again helps you in improving your efficiency. Because you have got data, you will realize whenever you run inefficiently, which will lead to perpetual optimization. As I said, you need to optimize at various load points, and only if you are aware when did you run efficiently and when did you not run efficiently can you think about optimization. So this real-time measurement dashboards, fault analysis ultimately helps you in operating a plant well, in optimizing and achieving a lower kilowatt per ton. Not only achieving a lower kilowatt per ton, but even maintaining it continuously. and that's what an optimized plant looks like. So huge difference between whatever operating a plant at zero point 0.6 kilowatt per ton versus 1.2, but that's happening in the field. So since you guys are maybe just coming into the HVAC industry or would be coming, I'm telling you an opportunity. In operations in HVAC systems, there is a lot of inefficiency which we should address if we are so concerned about climate change, about sustainability. We must address this. So that brings me to the end of my presentation, and probably this is the time we can start taking questions. So I'm going to look at this question block here. I'm just going to see how I can oops. Well, I'm just trying to Chetan, hello.
Yes, sir.
How do I increase, how do I pull this? I can't read the question.
Okay, 1 minute, sir. So, are you able to see that question tab now?
Yes,
Just below the poll.
yes, I can see the tab, but I don't know how do I make it larger?
Okay, 1 minute. Just a minute, sir. I'll tell you.
Uh, okay, let me go.
Yeah.
Let me go step by step. Whatever I can see, I'll keep answering.
Yeah.
Uh,
Yes.
so there's a question how the system detects the amount of return air to be mixed with fresh air and some will be exhaust. Okay, good question. So most of the buildings, what's happening is I they might have some sort of a demand control ventilation. That means what they will do is they will measure the CO2 level of the return air. So they will understand how the CO2 levels are going up in the space, in the occupied space. So based on that, you've got a fresh air VAV box, and you're opening it and you're allowing more fresh air coming in. So more fresh air comes in, mixes with this return air, and you try to maintain CO2 levels within a certain limit. To tell you about that limit, outside CO2 is supposed to be about 400 ppm, and the inside in a building, you don't want the CO2 to go more than plus 700, which means not more than 1100 ppm. So that's one way of doing it. What about exhaust? Mostly, the exhaust which is there in a building is nothing but the toilet exhaust. So that's the exhaust. And what we are trying to do is we always want the amount of fresh air that we are getting into the building is more than the amount of exhaust air. Why do we want that? We want that because the buildings can be pressurized. Why do we want that? So that there is no infiltration. Infiltration as a load is difficult to address, and it spoils the inside conditions. All right.
So,
We have
if
experienced,
you
yeah.
see, yeah, if you see, there is a in the question tab there is a cross sign and a
Yeah.
box with the arrow. So when you click on the box, I mean showing arrow, so you will be able to see the big screen of questions.
Well, I'm trying.
Questions tab. Then in the right side there is a cross tab and a box.
Right.
So click on that box.
Well, anyways, let me just. According to you, which AC? I'm just going to keep reading the questions which I can see, and I keep
Okay.
answering.
Yeah.
And
Yes.
maybe you can see if I've missed out on any question and let me know.
Sure. I'll
All
let
right.
you know. Yes.
So according to you, which AC is better, inverter AC or scroll AC, considering financial and power consumption? Well, AC. Which AC are you talking about? Are you talking about a split air conditioner? Uh, basically, I mean, all my experience is more on central plants. But based on what I know, I mean, if you are using a split air conditioner in a bedroom, wherein probably you want to use it throughout the night, which basically means varying load conditions. Having an inverter split is going to be much better as compared to having a normal split. A normal split has got an on-off compressor. But suppose that same split is now installed in your drawing room and you use it sparingly. So whenever there's a party, probably that's the time when you use it. A lot of people there. So what happens in that unit? You run it very less, and whenever you run it, it's almost running at full load. I mean, it doesn't really get a chance to unload. So for such kind of application, not having an inverter will also make sense. Okay, but for chillers, mostly it makes sense. All right, challenges in VAV boxes. I've faced a lot of issues with VAV boxes. Yes, and it's not only true for VAV boxes. To be frank, I use the term system level commissioning, and I'll be honest with you. In my so many years of experience, I mean, have to see that buildings were really commissioned properly. HVAC systems were really commissioned properly as a system. We just have chiller being commissioned and this equipment being commissioned. We are still talking about equipment level commissioning and not system level. Coming to the challenges with VAV box. Um, uh, well, um, whether using a pressure independent VAV box or not, communication of that VAV box, um, uh, uh, where do you put your static pressure sensor? Are you, in your BMS system, have you even connected the VAV boxes so you understand that, the position of your VAV boxes, and ultimately you can do something called a duct pressure, static pressure reset? Well, I mean, it's a very general thing. I mean, how do I talk more about it? Yes, there can be issues, but I guess most of the issues are more related to the person who has, supplied those VAV boxes are not able to give you support properly. But otherwise, it's not high tech. I mean, uh, that's what I can say. All right. As most of the abbreviation, as water is becoming precious, cost of kilowatt per ton is high in water cooled when compared to air cooled. So you agree with air cooled? Well, not really. My whole presentation was telling you that, indirectly telling you that water cooled is more efficient, and it's a fact. And why is that? Two reasons for it. One is an air cooled system obviously works based on the ambient air dry bulb temperature. A water cooled system works on the wet bulb temperature. So one, wet bulb temperature is always lower than the dry bulb temperature. One. Second, this heat transfer between the refrigerant and the air is very poor. The heat transfer coefficients are very poor. So if you do an air cooled condenser, your approach temperatures, the approach is nothing but what's the temperature at which the ambient air was coming into the condenser versus what's the temperature at which the refrigerant was condensing. This approach is very high, to the tune of 25 to 30 degree Fahrenheit. For a water cooled chiller, the approach, which is nothing but the difference between condenser water outlet temperature and the condensing temperature, is in many designs 2 to 3 degree Fahrenheit. Now, the COP of a chiller, you're aware that a chiller is the equipment which consumes the maximum amount of power, is a lot dependent on lift. And if you are going to make a compressor work harder, which is go to higher condensing pressures, the power consumption is hugely different. Give you an example. Standard tender conditions, Delhi-like conditions, wherein it's 90 degree Fahrenheit chilled water condenser cooling water inlet, the chiller power consumption is 0.65 to 0.7 kilowatt per ton at full load design condition. Water cooled chiller, air cooled chiller is 1.4 to 1.45 kilowatt per ton, almost double. So without a doubt, water cooled is more efficient. Now, to answer your question, water is becoming precious. Well, to be frank, water is precious, no doubt about it. We are not managing our water resources well. We are wasting water, and that's why water is becoming precious. But to be frank, enough water is available. I even remember a site in Manesar wherein people were evaluating this very question. Hey, even water is not there. Should we use air cooled? And that site was 10 acre in total. 8 acres was hard and 2 acres was soft. The consultant calculated the amount of rainfall which is going to fall on the hard surface. He calculated that probably 80% of that he can capture. So rainwater storage is what I'm talking about. And ultimately, the calculation showed just based on rainwater, he will be in a position to meet 80% of his water requirement for the water cooled plant. So I don't really believe that water is not available. I really believe that we are wasting water and not using it better as a resource. Okay. Could you please tell me something about phenolene capillary? Don't mind if the spelling is wrong. Capillary tubes. Well, capillary tube is a kind of an expansion device. Again, this is what is used in smaller equipments like, say, a refrigerator, maybe even a window AC. My experience has been more with central plants and larger equipments. A window AC is like 1.5 ton. When we talk about central plants, we're talking about 200 tons, 300 tons, and even larger. So probably I won't be able to talk more about capillary tubes. I'm not really in that field. I'm in the field of central plants only. All right. As most of the abbreviation I can't understand. Well, I've highlighted, answered that. VAV boxes. Can you elaborate why the design delta T is not being achieved in airside? Good question. The design delta T, probably you're talking about chilled water. Why would the delta T of chilled water get spoiled? Various reasons for it. One reason we can very well understand is with time, the cooling coil might get fouled. So if the cooling coil is getting fouled, that means it is not in a position to do that much of heat transfer. And still to achieve that supply temperature, the valve opens more and it allows more flow and the delta T comes down. So one of the reasons is going to be fouling of cooling coil. Second is going to be you might have designed the system with a set point of 75 degree Fahrenheit, but you're trying to achieve 70 degree Fahrenheit. So whenever you try to push the set point down, your delta T gets spoiled. You might have leaky valves wherein maybe half your building is working and half is not. And the half which is not working, the valves are supposed to be closed. But if they're not closed, they are bypassing some water. You might have some three-way valves, which is again going to lead to mixing. You might have these valve actuators which are not sized correctly. There's something called valve authority. So if you don't have that, what is happening is valve is hunting, especially at lower loads. So at lower loads, valve is hunting. Suddenly the flow goes up, suddenly the flow goes down, delta T gets disturbed. Uh, well, I mean, these are the top of the mind reasons that I can tell you. We have experienced one of the best sessions. Oh, thank you so much. uh, there's another question on what I would like to know is how much of artificial intelligence used in this and how effective. Okay, that's the future. When I'm talking about putting all these measurement devices, I'm talking about you gathering all the data. Why am I saying so? We've got this thing. I mean, I used this phrase somewhere in the presentation. You cannot manage what you don't measure. So what is artificial intelligence going to do? Whatever gets measured gets improved. That's what it's going to do. Because you have data, because you will know when you're efficient, when you're not. Probably you're in a position to tickle or tweak the system to run your whole system more efficiently. Give you an example. To be frank, for the sake of efficiency, the standard logics were PID logics, proportional, integral, derivative. It's a kind of a controller. We have in HVAC systems, people are now talking about relational logics, which is all to do with data, which is all to do with tweaking continuously, which is and hence achieving the best efficiency, and that's all to do with artificial intelligence. So yes, artificial intelligence has got a huge scope. IoT devices, data analysis is going to make HVAC system more efficient. Do we have a mechanism in place wherein data from a set of sensors used to properly test, adjust, balance the entire system in real time? Well, as I said, I mean, that's what I'm saying. You can have your standard logics, but you can have a higher level logic sitting on top of that central logic, standard logic, which is tweaking the system and trying to run it at its most efficient point all the time. Uh, would you balance? The word balance, once we are talking about putting VFDs everywhere, this word has become redundant. The more important word is resets. Give you an example. Chilled water pumping. You're supposed to have a DP, and the chilled water pumping is supposed to work based on that DP. ASHRAE 90.1 talks about you should do a DP reset. How do you do that? Based on your valve positions. If you've used VAV boxes, and if you've used a duct static pressure sensor, again you're controlling the fan based on the duct static pressure. Do you know that the duct static pressure is not supposed to be a fixed value? You're supposed to reset it again. Why? How do you do that? By again the position of the VAV boxes. So yes, that's required. All this is optimization. Does automatic tube cleaning system ball type help in reducing optimizing condenser fouling? Chiller size is 300 tons. Very specific question, but let me answer you. Automatic tube cleaning system will maintain condenser approach at a lower, will maintain lower condenser approach, which is good because your chiller efficiency will get improved for sure. But please understand that automatic tube cleaning system is now keeping your condenser clean. But if you're only bothered about condenser and not about cooling tower, now what happens to efficiency if your cooling tower is fouled and your condenser water inlet temperature is higher? Your automatic tube cleaning system is not going to do anything about that. So water treatment is important. Second, your automatic tube cleaning system is just focused on fouling. Your water treatment is required even to protect yourself from corrosion. So yes, it's a good add-on automatic tube cleaning system, but it's not a replacement of water treatment. And don't be just chiller focused. Look at your complete system, uh, especially cooling towers. And I'll tell you, they're the most ignored equipments in the whole HVAC system. And if your cooling tower is not working well, it is affecting the efficiency of your whole system. All right. Does piping heat loss impact much in central plant? Well, not really. I mean, people are doing district cooling plants. You know what is district cooling? It's being done in Middle East, which is supposed to be a pretty hot place, and they've got kilometers of piping. And do you know how much is the heat loss because of these kilometers of piping? 3 to 4%. When we talk about a building, it's going to be 1 to 2% at max. So it's not we're not having a huge in heat gain because of bad insulation. We're not. That's not true. For commercial AC units, which type of cooling is efficient, VCC or VAC? I'm not sure what that is. VAC? I'm not sure. I'm very sorry. I don't understand your question. For conditioning the room, we employ supply ducts for supplying the air, but for sealing suspended units, the return air ducting is not employed, and it can directly suck in return air and transfer to the HU. How do we determine the exact amount of air that is being returned to the HU? Well, whatever is being returned to the HU is whatever is being supplied by the HU. Now, how do you determine the airflow rates? Pretty simple, by using a device called an anemometer. So go ahead, take the anemometer and take the readings on the filter, and you will understand how much is your airflow rate. And your return is the same as your supply. I hope I'm answering your question. Maybe you wanted to ask something else, but I'm not sure what. From an economic point of view, which chiller system is preferable, air or water? Water. Good evening, sir. We are from Walchand Institute of Technology. My question is how to minimize the heat dissipated by the compressor, which are increasing the average global temperature of the Earth. Heat dissipated by the compressor. Ah, Mm. So what you're saying is that because I'm using an air conditioning system, because I am dumping the heat ultimately to the atmosphere, the temperature is increasing. Well, the atmosphere is a huge heat sink, and that's the way an air conditioning system works. There is no other way. Is that causing temperature increase? Well, not really. If you really uh, Google and look at climate change and what's the reason for climate change, it's going to be CO2 emissions. It's going to be we removing our green cover. It's going to be so much of use of petroleum products. So I don't know, what exactly you wanted to say, but I'm going to highlight another thing, which is comfort air conditioning a luxury? Well, not really. If you are trying to do knowledge work, why are we doing comfort air conditioning? We are doing that to make people more productive. It's no more a luxury. It's really to help a person sitting in a space be more productive. And this is how the economy works. We're going to be more service oriented, less of manufacturing, less of agriculture. It's going to be more service. It's going to be more buildings, people working out of buildings doing knowledge work. Comfort air conditioning is going to be basic, but we need to be much very conscious about running these HVAC systems more efficiently. That I totally agree.
Hello.
Yes.
I think we are out of time, and I request everyone. I mean, whoever is having questions, they can mail to Sandeep sir. The same mail is available on the screen, right?
Right.
Yeah, right. Thank you for joining webinar. Looking forward to your continuous participation. Thank you.
Okay.
I give the call to Sandeep sir. Sandeep sir, please.
Okay, thank you so much, everybody, for attending this webinar, and I hope it was useful for you and a good investment of your time. If you have any more questions, please feel free to contact me at my email ID mentioned here. And tomorrow is Republic Day, and I wish you all a very happy Republic Day. Jai Hind. Thank you.
Jai Hind. We are closing the webinar. Thank you, everyone.
Bye.